Let's explore grounding metal raceways within separately derived systems, or SDS, according to the 2002 National Electrical Code. We'll be examining 4 distinct scenarios, each involving 4 sets of 600 kc mil conductors installed in 4 separate raceways. These raceways run between a transformer enclosure located at doors and an overcurrent protective device, or OCT, situated approximately 30 feet away inside an adjacent building. Scenario 1 features the bonding jumper, or BJ, positioned at the transformer's ZO location. The 4 raceways utilize a metal, specifically rigid metal conduit, or RMC, 90-degree bend at each end, connecting to a run of rigid non-metallic conduit, or RNC. In Scenario 2, the bonding jumper is located at the overcurrent protective device. Similar to Scenario 1, the 4 raceways have a metal RNC 90-degree bend at each end of an RNC run. Scenario 3 places the bonding jumper at the transformer's ZO location. However, in this scenario, all 4 conduit runs are entirely RMC. Scenario 4 has the bonding jumper situated at the overcurrent protective device location, and all 4 conduit runs are also entirely RMC. Now let's address the key questions. What size conduit bonding conductor is required, if any, and how do we accomplish the proper grounding of the metal portions of the raceways in each of these scenarios? We will refer to relevant sections of the 2002 NEC to provide substantiation. In Scenario 1, where the bonding jumper is at the transformer ZO location and the raceways consist of RNC elbows connected to RNC runs, a conduit bonding conductor is required. The recommended size is 2 American wire gauge, or AUG, copper. To properly ground the system, connect the 2 AWG copper bonding conductor to the ground bar within the transformer enclosure. Then connect the metal raceways, that is, the RMC elbows, to the bonding conductor at each end of the run. This connection should be made using a bonding bushing or another approved means designed for this purpose. In Scenario 2, with the bonding jumper at the overcurrent protective device and similar RMC to RNC raceway construction, we again require a conduit bonding conductor. A 2 AWG copper conductor is suitable. Grounding is achieved by connecting this bonding conductor to the ground bar in the overcurrent protective device enclosure. Similar to the first scenario, the metal raceways, the RMC elbows, must be connected to the bonding conductor at each end of their run, again using a bonding bushing or an equivalent approved method. Now for Scenario 3, where the bonding jumper is at the transformer ZO location and all 4 conduit runs are RMC, a conduit bonding conductor is not required. The metal raceways are inherently grounded to their direct metallic connection to both the transformer enclosure and the overcurrent protective device enclosure. These connections provide the necessary grounding path. Finally, in Scenario 4, with the bonding jumper at the overcurrent protective device location and all conduit runs being RMC, a conduit bonding conductor is likewise not required. In this configuration, the metal raceways are grounded through their direct connection to the overcurrent protective device enclosure, ensuring a continuous grounding path. To substantiate these recommendations, let's refer to specific sections of the 2002 National Electrical Code. Firstly, NEC Section 250.30. A1 mandates that metal raceways, cable trays, cable bus, and other metal enclosures for a conductor shall be grounded. This is a fundamental requirement for electrical safety. Secondly, NEC Section 250.30. B states that conduit tubing and other raceways shall be securely connected to ground where practicable. This section emphasizes the importance of a reliable ground connection for raceways. Thirdly, NEC Section 250.30. C addresses bonding jumpers, stating that bonding jumpers specified in 250.30. A1 shall be connected to the grounding system in accordance with 250.28. This ensures the proper connection of bonding jumpers to the overall grounding system. Lastly, NEC Section 250.28 provides guidance on the connection of grounding electrode conductors. It states that where connected to a grounding electrode, the grounding electrode conductor shall be connected to the grounding electrode system as near as practicable to where it enters the building or structure. An exception to this rule allows the grounding electrode conductor connection to be made at any accessible point on the grounding electrode system where the building or structure is served by a grounded electrical system and a grounding electrode conductor is connected to the neutral of the grounded electrical system. In summary, the need for a conduit bonding conductor depends on the type of raceway used and the location of the bonding jumper. When non-metallic conduit is part of the raceway system, a bonding conductor is generally required to ensure a continuous grounding path. However, when all raceways are metal and properly connected to grounded enclosures, the raceways themselves provide the necessary grounding, eliminating the need for a separate bonding conductor. Always adhere to the applicable electrical codes and standards to ensure a safe and compliant electrical installation. The size of the grounding electrode conductor is determined by NEC Table 250.66. The size of the equipment grounding conductor is determined by NEC Section 250.122. When installing or maintaining electrical systems, always prioritize safety and consult with qualified professionals. Proper grounding is crucial for protecting people and equipment from electrical hazards. Now, let's delve deeper into the specifics of selecting and installing bonding bushings, a critical component in ensuring effective grounding of metal raceways. A bonding bushing is a specialized fitting designed to provide a reliable electrical connection between a metal conduit or raceway and a metal enclosure, such as a transformer enclosure, a junction box, or an overcurrent protective device enclosure. Its primary function is to maintain a low impedance ground path, which is essential for safely carrying fault current back to the source in the event of a ground fault. This low impedance path helps to quickly trip the overcurrent protective device, such as a circuit breaker or fuse, minimizing the risk of electrical shock and equipment damage. Bonding bushings come in various sizes and materials to accommodate different conduit sizes and environmental conditions. They typically consist of a metallic body with an insulated throat to protect conductors from abrasion and a means for connecting a bonding jumper. The connection method can vary, but common types include set screw connectors, lay-in lugs, and threaded hubs. When selecting a bonding bushing, it's crucial to choose one that is specifically listed and labeled for grounding purposes. Look for markings from recognized testing laboratories, such as Underwriters Laboratories, or all or other approved certification organizations. This ensures that the bushing has been tested and meets the applicable safety standards. The size of the bonding bushing should be appropriate for the size of the conduit it will be used with. Using an undersized bushing can compromise the grounding connection, while an oversized bushing may not fit properly or provide a secure connection. The material of the bonding bushing should also be compatible with the materials of the conduit and enclosure it will be connected to. For example, if the conduit and enclosure are made of aluminum, an aluminum bonding bushing should be used to prevent galvanic corrosion. Installation of bonding bushings requires careful attention to detail. Firstly, ensure that the surfaces of the conduit and enclosure are clean and free of any dirt, rust, or other contaminants that could impede the electrical connection. Secondly, install the bonding bushing according to the manufacturer's instructions. This typically involves tightening set screws or threaded connections to a specified torque to ensure a secure and reliable connection. Thirdly, connect the bonding jumper to the bonding bushing using an appropriate connector. The bonding jumper should be sized according to the applicable electrical code requirements, typically based on the size of the circuit conductors. The length of the bonding jumper should be kept as short as possible to minimize impedance. In situations where multiple conduits enter an enclosure, each conduit should be bonded to the enclosure using a separate bonding bushing and bonding jumper. This ensures that each conduit has its own dedicated grounding path. It's also important to inspect bonding bushings periodically to ensure that they are in good condition and that the connections are tight. Over time, vibration, corrosion, or other factors can loosen connections or damage the bushings. Any damaged or deteriorated bonding bushings should be replaced immediately. Now, let's consider the specific requirements for grounding metal raceways in separately derived systems, or SDS, as outlined in the National Electrical Code, or NEC. A separately derived system is an electrical system that derives its power from a source other than a direct connection to the utility grid. Common examples of separately derived systems include generators, transformers, and solar inverters. The NEC has specific requirements for grounding separately derived systems to ensure electrical safety and prevent ground faults. The general rule is that separately derived systems must be grounded in accordance with NEC section 250.30. This section requires that a grounding electrode conductor be connected to the separately derived system's neutral point, or neutral conductor if one exists, and to a grounding electrode. The grounding electrode conductor must be sized according to NEC table 250.66, based on the size of the separately derived system's conductors. The grounding electrode must be one of the types specified in NEC section 250.52, such as a metal underground water pipe, a concrete encased electrode, or a ground ring. In addition to grounding the separately derived system itself, it's also important to ground any metal raceways that contain conductors of the separately derived system. This is typically accomplished by bonding the metal raceways to the separately derived system's grounding system. As we discussed earlier, bonding bushings are commonly used to provide a reliable electrical connection between the metal raceways and the metal enclosures of the separately derived system. The size of the bonding jumpers used to connect the metal raceways to the grounding system must be sized according to NEC section 250.102. It's also important to ensure that the metal raceways are properly supported and secured. The NEC has specific requirements for supporting and securing raceways to prevent them from becoming damaged or dislodged. In damp or wet locations, it's important to use corrosion-resistant materials for the metal raceways and bonding hardware. This will help to prevent corrosion and ensure a long-lasting and reliable grounding system. When working with separately derived systems, it's crucial to follow all applicable electrical codes and standards. This will help to ensure safe and compliant electrical installation. Always consult with qualified professionals if you have any questions or concerns. Let's talk about the importance of maintaining a low-impedance ground path. The concept of a low-impedance ground path is paramount in electrical safety, especially when dealing with fault currents. Impedance, in this context, refers to the opposition to the flow of alternating current, encompassing both resistance and reactance. A high-impedance ground path hinders the rapid flow of fault current, potentially delaying the operation of overcurrent protective devices like circuit breakers or fuses. This delay can lead to several undesirable consequences. Firstly, it increases the duration of the fault, raising the risk of electrical shock to individuals who may come into contact with the energized equipment. Secondly, prolonged fault current can cause significant damage to electrical equipment, including conductors, insulation, and enclosures, due to overheating and arcing. Thirdly, a high-impedance ground path can create voltage drops along the ground path, leading to objectionable neutral currents and potential malfunctions of sensitive electronic equipment. To ensure a low-impedance ground path, several measures must be taken. Firstly, all grounding conductors, bonding jumpers, and connections must be properly sized and installed. The size of these conductors should be based on the available fault current and the requirements of the National Electrical Code. Connections must be clean, tight, and free of corrosion to minimize resistance. Secondly, the length of grounding conductors and bonding jumpers should be kept as short as possible. Longer conductors have higher impedance due to their increased length and inductance. Routing grounding conductors in a straight and direct path also helps to minimize impedance. Thirdly, metal raceways and enclosures should be properly bonded together to create a continuous grounding path. Bonding bushings, as previously discussed, play a crucial role in this process. Fourthly, the grounding electrode system should be properly installed and maintained. The grounding electrode system provides a connection to the earth, which serves as a reference point for the electrical system. A low-impedance connection to the earth is essential for dissipating fault current and preventing voltage buildup. Periodic testing of the grounding electrode system is recommended to ensure its effectiveness. In addition to these measures, it's also important to consider the overall design of the electrical system. Minimizing the distance between the source of power and the load can help to reduce impedance. Using dedicated equipment grounding conductors instead of relying on the metal raceway as the sole grounding path can also improve grounding performance. Proper grounding is not a one-time task, but rather an ongoing process. Regular inspections and maintenance are essential to ensure that the grounding system remains effective over time. Any signs of corrosion, loose connections, or damaged components should be addressed promptly. By maintaining a low impedance ground path, we can significantly reduce the risk of electrical shock, equipment damage, and other electrical hazards. Finally, we will review NEC 250.30 Section A1, B and C, and 250.28. Section 250.30 covers grounding requirements for separately derived systems. 250.30 A1 states metal raceways, cable trays, cable bus, and other metal enclosures for conductors shall be grounded. This ensures that any fault current flowing through these metal components has a lower impedance path back to the source, allowing overcurrent protective devices to operate quickly and safely. 250.30 B discusses conduit, tubing, and other raceways shall be securely connected to ground where practicable. This emphasizes the need for a reliable connection between the raceway system and the grounding system. 250.30 C bonding jumper is specified in 250.30. A1 shall be connected to the grounding system in accordance with 250.28. This ensures that the bonding jumpers used to ground metal raceways are properly connected to the overall grounding system. NEC 250.28 describes grounding electrode conductor connections, stating that where connected to a grounding electrode, the grounding electrode conductor shall be connected to the grounding electrode system as near as practicable to where it enters the building or structure. This emphasizes the importance of making a direct and effective connection to the grounding electrode system to provide a low impedance path to ground. The exception permits that where the building or structure is served by a grounded electrical system and the grounding electrode conductor is connected to the neutral of the grounded electrical system, the grounding electrode conductor connection to the grounding electrode system shall be permitted at any accessible point in the grounding electrode system. This provides flexibility in locating the grounding electrode conductor connection, as long as it is accessible and provides an effective grounding path. These sections of the NEC work together to ensure that separately derived systems are properly grounded, minimizing the risk of electrical shock and equipment damage. By following these requirements, electrical professionals can create safe and reliable electrical installations,